Hello, everyone. My name is Charaf ZGUIOAR. I am happy to be part of this global PyData event. I'm going to talk to you about optimal binning in logistic regression and in regression models more generally. Um, we're gonna start by a word about my background and a little bit about and the agenda about what we're gonna talk about today. So I work as a data scientist at BNP Paribas in Paris, France. I've been working there since 2023. I am also a lecturer at the Sorbonne School of Economics, and I'm happy to report that my students are very bright this year. Uh, I've worked in the past in treasury risk management and in the pharmaceutical industry. Funnily enough, I've been a PyData Paris lurker for the past 2 years, 24 and 25. And this is, believe it or not, my first time speaking at any PyData event. And for the next year, I'm thinking about doing a PhD. So if there are any folks in the audience who have done a PhD in that, feel free to reach out by the end of this talk. I would be interested to talk to you. Um, Back to our subject, I'm just gonna make a disclaimer. All the views are gonna be expressed here on my own and do not represent any of my employer or any institution I'm affiliated with, and all the examples are based on public data. Oh, my slides just went a couple of slides further. I was going to start by this one and talk about modeling under operational and regulatory constraints. As you know, finance and healthcare are deeply regulated sectors with outside regulators looking on companies within these areas and also internal watchdogs that make sure to review the models with internal validation teams and structures of independent review to make sure that the models that are deployed are used reasonably, um, that are used where they make sense, and to minimize any harm or financial losses that might be caused by the erroneous use of models. I came up with two examples. The first one is you've probably heard about is the London whale. It's a value at risk model that estimates the worst financial loss an institution can undergo in one day of trading, for example, or over a specific horizon. And the story basically goes that the model was very miscalibrated and it ended up causing blowing a huge hole in the financials of JP Morgan. And JP Morgan at the time also was the subject of a fine by the regulator because of that. Um, and on the right hand side, I have an example of not not related to models per se, but more to the structures of independent review, where we have a case of some of a doctor who had fake credentials uh, and was conducting cancer research, and the failures of those independent review structures and checks and balances ended up causing harms and losses to individuals and also to the university that this person was affiliated with. So the message here is that model risk is very important, and if models are used incorrectly or poorly implemented, that that can cause huge losses. And the subject here that you might have noticed in the title, logistic regression, you might ask yourself why. Well, in the 1980s and 80s and 90s, logistic regression made sense from a computational perspective due to the ease of estimation using maximum likelihood. And also, it's easily explainable. But the issue is that the logistic regression assumes a linear relationship between the log odds and the predictors or the explanatory variables. But as you know, in reality, not most relationships that we have with our dependent variables are not linear. So how do we handle that? Well, that's where binning comes to the picture. Uh, I had this slide just as a review of the basics behind logistic regression. So basically, we modeled the probability of y being equal to 1, given some features x. And we build a linear score, beta 0 plus the beta transpose multiplied by x. Then we pass it through this S-shaped function, sigma, to turn it into a probability between 0 and 1. Equivalently, if we look at the log odds, the log of p over 1 minus p, that's exactly equal to beta 0 plus beta transpose x. That's why we say the logistic regression is linear in the log odds. The main takeaways are the model assumes a linear relationship between the log odds and the features, as I said. And second, each coefficient translates into an odds ratio. For example, if the beta j is equal to 0.7, then increasing x by 1 unit multiplies the odds by the exponential of 0.7, which is roughly a factor of 2. And finally, logistic regression is fantastic when the log odds versus the feature is almost linear. And that's a key assumption that we're going to challenge. And that's where binning comes to the picture. This is a very informal definition of binning. I took this screenshot from from the South African coronary heart disease data set. As you see, there's an age column that is a quantitative variable, and if we decide to bin it, that will basically just be discretized into categorical variables. For example, we know that the individual 259 has an age between 31.5 and 50.5. That's the rough idea basically behind binning. A couple of housekeeping items that we're going to need are the weight of evidence and the information value, and I think it's a good idea to talk about them because we're gonna use them later on. So the high level idea is that we need a way to encode those bins and to make sure to be able to measure how useful they are. um, credit scoring, for example, people use the two classic tools, the weight of evidence and information value. Uh, for example, we have a variable, we split it into bins, and for each bin j, we look at how the proportion of good and bad behaves. We have a variable, we split it into bins, and for each bin j, we look at how the proportion of good and bad perform, specifically when the share of specifically when the share of goods in this bin is relatively high compared to the rest of the bins. And we can say the same thing with respect to the respect to the bad bins. If it contains more bads than goods, then the ratio is going to be less than 1, and the log is negative. The bin is bad leaning, so the weight of evidence is literally how much evidence in log odds units that this bin gives in favor of good versus bad. And the nice trick is that once you replace each bin by its weight of evidence, the relationship between the variable and the log odds becomes much more linear. On the information value front, if the weight of evidence tells us something about each bin within a feature, the information value tells us about the whole variable. And it's computed by summing over all the bins, the share of good minus the share of bad, weighted by the weight of evidence. If the and we can use specific thresholds for the information value to be able to choose predictive features. Um, for example, if it's inferior to 0.02, it's not predictive. It's been 0 to 0.1, it's weak, and so on. Um, when the log odds are not linear, I've put a graph here of the relationship between the observed probability of default, or probability of disease, for example, on the y-axis, and the age of a patient or a customer. And you can see that the relationship is not linear. For example, in terms of credit scoring, you can have young and old customers who are going to be riskier than people in their mid age. So that's something that we need to deal with in terms of bidding. Um, and a single beta cannot capture the whole thing. So that's why we need bidding. This is just a formal definition of bidding. I think we went over the explanation a couple of slides ago. I'm not going to spend a lot of time on this. I have uh, an illustration here of two models, Model A and Model B. Let's assume it's in healthcare. And this model is telling us basically what is the probability of a patient coming back to the hospital once he has left. Um, and the model gives us a probability, and that we basically cut into deciles, and the 10 being the worst decile. That means that that's the decile where the patients that are most likely to come back should be, as predicted by the model. And the percentages that you see are the empirical real life share of patients who ended up coming back. So if someone could put into, I'm not able to see the comments, but I would like to see if I'll probably put this in the other screen. But it probably would be a good idea if someone if someone could tell, write in the comments, what is the issue here? What is the main difference between Model A and Model B? Okay, I just opened the comments. I see that there's a question. I will try to take it at the end. That's true. That's true. Basically, they're going in opposite directions. They have different letters. That's true. Negatively correlated. That's true as well. Well, the Model A, given that we assume that our predicted decile is the worst, we would expect to have the highest share of bad of the of the patients who are most likely to come back in this decile. So, and even the increasing behavior of the share of risk, what we would call the risk rate, it's good behavior that you would expect from a model. On the other side, with respect to Model B, we've got something that is completely opposite. In the worst decile, that means that in the decile where patients are most likely to come back, there's a small share of patients who really ended up coming back. Naive binning. So we're gonna put our Sherlock Holmes hat, and I'm gonna investigate. Um, while Model B could have had a great AU area under the curve, a great Gini. The issue here it is more with respect to how the population has shifted in time, and how defensive would the bins are to take into account that shift. In model B, what I suspect, and that's how I tried to build it, is that I use naive build that I use equal width binning. Meaning that, for example, if we had an age variable, I just put in equal weights. I tried to put in each bin the same number of observations. So it's very naive way to do it, very basic, but better than none. But it goes to show the importance of binning. What we're gonna do together we're gonna go through the South African coronary heart disease data set. So number we have the variables here, and the cool thing about this data set is that it comes from a sector it comes from the healthcare sector, so there's a lot of regulatory constraints on this, as I said beforehand, and there's a lot of quantitative variables. So it means that we can do a lot of binning. So we got age, we got the systolic blood pressure, and we've got a categorical variable saying whether the person had a history of coronary heart disease or not, and a couple of others. So I focused only on one variable, basically the age, and I went about doing a basic decile binning, meaning or a quantile binning, meaning that I find on the for the age variable I find what are the deciles, the cutoff points, and I try to build my bins based on that. And as you can see, we get something that is downward trending in terms of the risk rate, which is a good sign. On the left hand, we do it on a trained sample, and on the right hand, we've got the test sample to see whether our bins really hold outside of the training. Looking at bins just in the in the training environment is not sufficient. I tried to do the same thing with equal width binning. That it means to try to put the same number of observations into each bin. You can see that it's slightly more noisier than the previous one, and that the risks are quite that the risk rates are quite different toward the riskiest deciles. The third one is that I used a decision tree basically to handle the binning. Um, but same story here, the pattern is not guaranteed to remain monotone or stable in the testing sample. And the last one and the last method is that I used optimized binning, and that's what we're going to talk about in the next slides. So we frame binning as an optimization problem that to maximize a specific metric. And that metric can be the Gini, it can be the AOC, and it can be any performance matrix basically for or stability in time if we're looking to maximize that. If we want to make sure that our model survives a long to be used to have a longer lifetime of use, we could maximize for that as well. Um, so what we're gonna do is that we're gonna try these four approaches that I showed you on all of the quantitative variables, and we're gonna use them to predict whether a patient has coronary heart disease. So the first approach, we're gonna use a classic logistic regression model with no binning. Second approach, we're going to use a logistic regression and we're going to add naive binning everywhere. Third method, we're going to try to compare how all of this performs compared to a boosting model. And the last thing is we're going to combine a logistic regression plus the optimized binning method that I just talked about. And here are the results that I was able to build on this data set. Um, you can see, first of all, that the logistic regression plus optimal binning approach has the highest AOC on the validation and on the test set. Uh, No, sorry, there's the raw regression that has the highest on the validation. And in terms of the test, it was the optimal binning that was able to hold. Um, while the logistic regression with no binning at all was able to get the highest score on this data set in the validation, and the highest on the validation set and the second highest on the test. Um, that's that's great. But it also depends on how all of this will hold in production. If we ever deploy this model into production, the stability of this model, of the raw model, is not sure. However, in the optimal binning, as I said before, we can optimize our bins for stability and for performance. Um, and that's what we're gonna see in the next slides. What I wanted to observe before moving on is that the light GBM model did not perform as good. I know that this was only on one data set. These metrics are not to be taken at face value, but the thing is the comparison between the light GBM and a logistic model that adds optimal binning. I know that boosting models they perform. I know that boosting models they handle binning differently by using a frequency approach. Um, Libraries like XGBoost, CatBoost, they use base learners inside the boosting ensemble. So each time a tree splits a feature, let's say x inferior or equal to t versus x superior to some threshold, it is effectively creating two bins for that feature. Values on the left of t and values on the right of t. So deeper trees keep slicing these intervals further. So you're implicitly binning the feature into many small regions. And when you stack many trees together, the final prediction is just the sum of all these trees. And some of the implementations they go even further and pre-bucketize features internally into histograms for speed. Um, the the thing is that it's not always perfect. First issue, these bins are model dependent. So if you change the hyperparameters, the depth, or just even the random seed, the splits can move, disappear, or reappear. So effective binning is not stable. The second issue is that there is no guarantee of monoticity or simple shapes. The relationship that we expect working in these regulated environments is a monotone relationship, for example, between blood pressure and heart disease. Um, so these monotone relationships can wiggle up and down in strange ways, um, just because many small trees aren't interacting. This is fine for pure prediction, but it's painful if you're looking for a clean and monotone risk curve. And finally, it's hard to explain and document. Instead of a small table with 5 or 10 human readable variables and bins, you have hundreds of trees and thresholds. So writing all of that into model document for auditors is not it's not the optimal thing. So in regulated settings, stable and monotone risk curve and a clear justification for each bin are essential. I was I'm gonna move to optimal binning. So far we've seen what it can achieve. Let's look at how uh, it frames the binning as an optimization problem. Um, so you take one feature X and a binary target Y, and we want to choose the best partition of X into bins. So formally, we pick bins that maximize some score. As I said, it could be the Gini, the AUC, or the PSI, the stability index, for example, or information value. But we don't let the algorithm do anything it wants. We impose constraints that make sense in terms of risk modeling. Each bin must have enough observations, for example. Each bin must have enough events in terms of bads and goods. Otherwise, the estimation would be too noisy. And the total number of bins is bounded so that we don't end up with 40 bins that nobody can explain. Optionally, we can force the probability that will be predicted to be monotone across bins uh, to be either increasing or decreasing. So binning becomes find the partition that gives the best score subject to all these constraints. There's the MDLP approach, which is an entropy-based discretization. The idea is to think of binning as a way to compress the joint distribution of X and Y. And you choose the cut points that keep as much information about Y as possible, while not making the description too complex. There's another approach that frames the problem as a mathematical programming based one. Um, Step one, we pre-bin the feature into many small intervals, for instance, equal frequency or equal width bins. And these pre-bins are like Lego bricks. Um, so we set up a mixed integer optimization problem that decides which adjacent pre-bins to merge. And the nice thing is that this is the optimum we find is global for the chosen objective and constraints. So if you say I want at most 6 bins and at least 30 defaults per bin, and the probability predicted must be increasing, the solver will find the best partition or just tell you that it's impossible. And the final approach, so we're fitting, we can still overfit. Uh, we can still overfit using the deterministic approach that I showed earlier. With a stochastic approach, we try to bootstrap the data to refit the binning many times, add some noise to the objective or constraint and refit, then we aggregate the results. What does this give us is that we can check how stable the cut points are across time if we're optimizing for stability. If the same cut point appears again and again, it's probably robust. If the cut point jumps around, we know that the variable with that region is unstable. So in a regulated setting, this is very valuable because you can say to the auditors, we didn't just pick these thresholds once, we checked that the same cut points appear consistently across resamples, and they're not artifacts or a single snapshot. So to conclude and to have an idea of what good looks like in terms of binning, um, is first of all to know what you're optimizing for, whether you're optimizing for stability, accuracy, or both. To make sure that you have a solid grasp of the nature of the relationship between your x's and y, um, and to figure out uh, whether the constraints that you have from the business, from the regulation impose on you something that is very explainable, and hence optimal binning and offers a way to have explainable features and cut points. Um, and the evidence is that good binning is boringly stable and easy to explain, because you end up with the list of your value with your features, and you can explain your model to anyone who asks. Uh, I'm not gonna get into the slides, but I will share something that's very good. It's this library called Opt Binning that was developed by Guillermo Navas Palencia. Uh, it's a library that offers all of the four approaches to optimal binning that I talked about earlier that are easily implementable in Python. And I would like to pay a tribute to the person who maintains this library. And this library is open source, so you can use it and test it on your models. And I had a failure just a couple of minutes ago because I wanted to add the QR codes, and I wasn't able to do it on. I wasn't able to do it on Overleaf. So I will put in the chat the GitHub where I will put the slides and the code, and you can feel free to get in touch. You can feel free to get in touch with me on LinkedIn, and I thank you very much for your attention. And if there are any questions, I am more than happy to answer them. I'll try to take a look at the chat if I miss anything. Okay, there's a question. Dichotomizing a continuous variable like age leads to loss of information and reducing variability and statistical power. Did you consider categorizing age using a clinically meaningful point? Example, pediatric below 17, adult 1864, and senior above 64. In the example that I used, I showed the 4 approaches. If I go back to the slide, um, uh, in the equal binning, I think the smallest in the equal width binning approach, the minimum in the minute the minimum age was 15. So what I tried was just basically different approaches. I did not consider I did not consider I did not consider categorizing age using clinically meaningful cut points. What I wanted to do is to show the 10 bins, the 10 deciles, to make sure to see how the risk rate evolves across deciles. Visually, it makes sense, but I agree with you that in terms of in a clinical setting, using 10 or 5, it might not be the best approach. You would need definitely to find meaningful cut points that are relevant clinically.